and it's like it's in main person in the French collaboration and all. So we expect all the support in the future also. So thank you very much. So, sir, you can start your talk now.
Okay, thank you. Thank you very much. It's for me a great pleasure to talk again in KSOM. Last time I remember we were all with Professor Narasimhan and a nice garden. We had a beautiful dinner. And it's only unfortunate that we can't be all in Kerala again this time, but never mind. With technology, we are almost there. So I'll try to discuss about conjectures by Daniel Bertrand and Michel and Rodriguez Villegas on subgroups of unit groups. So I'll first discuss the problem, put it in perspective, and then we shall describe the results we got. So let me try to share the screen. So this is the one. Okay. What is the issue? So these questions are in fact interpolation between the classical lemma problem, say for units. You can do the same thing for S units, but we'll not discuss that here. But we'll concentrate on units. So they form a lattice with provided that you kill the rules of one, and this is done classically. It's another undergraduate class in number theory via the logarithmic embedding. And recall that. So we'll first concentrate on rank one subgroups. You just take one unit. So we fix a couple of notations. We take a number field, and you fix the degree, and you take some alpha in the multiplicative group minus the torsion. That is just some any non-zero algebraic number in K. And the lemma problem can be stated as follows: the white height is at least some constant divided by the degree, and the height is just the usual white height. It is, in fact, best possible provided that you frame it in this way, just using the degree of the field generated. Because you can have an easy example. You take the dth root of 2, and you get, sorry, there's a misprint here. It should be right log 2 over d. You should correct that thing. But apart from that, it's statement is correct. You can also take other examples, like theta is root of xd plus x plus 1. Choose d so that's you can easily prove it's irreducible. And then you get that the height of theta is less than log 3 over d. So you have many examples, not only coming from cyclotomic fields, where the growth is less than 1 over d up to a constant. But of course, you can have much stronger versions, provided that you have something finer than the degree as the parameter. So one such example is the following. This is a constant, again for alpha not in the torsion subgroup, such that the height of alpha is bigger than a constant divided by the degree over the maximal abelian extension, and not only over just the base field Q. Okay, so of course this statement would claim that over the maximal abelian extension, the height is bounded below, which is known. It's a result of Amoroso and Duarnichich.
Sinnou, I do not see your screen.
Oh, it's not shared? What happened?
It's on. Oh, now it is.
Okay. Okay. It has come back?
Yes, yes.
Okay, excellent. So in case you have not seen it, there is a misprint here for the height of 2 over 1 over d. It should be right log 2 by d. Okay, so now I turn to the regulator. So I first recall the notations. We take the logarithmic embedding. You go from the units to r to the number of places, which is the real places, plus 2 plus the number half of the complex embeddings. And you pair the complex embeddings using complex conjugation. And you define sigma k to be the R1 plus R2. And you just take the log of the absolute value of the unit, multiplied by 1 or 2, whether depending on whether the place is real or complex. So under this map, so this is directly the unit maps to a discrete subgroup of rank just Rk, which is sigma k minus 1. So it's a lattice of the hyperplane of equations sum of xi. And this is thanks to the product formula. And the kernel of the map is precisely the torsion subgroups. So you actually kill the roots of unity and you have the full thing. Okay. So now you can reframe the lemma problem in terms of the norm, L1 norm. Just take the L1 norm, using again the product formula, you see that the norm of a given unit is 2d times the height of epsilon. And so lemma problems just claims that the L1 norm is bounded below. Okay. So up to a normalizing factor, the regulator for itself is just, so maybe I should have put the definition, so it's not there. So maybe I'll do that quickly. So the co-volume, what happened? Just 1 second. So the co-volume of L of UK is just the determinant of the log of epsilon v I.
No, we do not see. We do not see the screen.
Okay, let us do it again. Yeah.
Yeah, good. Thank you.
So log of the determinant of epsilon v. So what you do is you take just all the v's which are a chosen set of complex embeddings mod the conjugation and the real places, and you take for epsilon I any basis of UK mod torsion. Okay. So now let us go back to the slides. And with this definition, there is a classical normalization which is for historical reasons. The regulator is the score volume divided by the square root of sigma k. Okay. Probably in modern days we would have defined the regulator as just the co-volume, but we are not going to change conventions that are essentially a century old. So what we know? We know since Zimmert that the regulator is at least exponential of complex of c times t, constant times t. And so if you remember Kumar's talk, discussed as the regulator as the mysterious part, and he concentrated on the class number, which is here, h of e. And so if you remember Kumar's talk, he told you that the log of h times r is equivalent to the log of the square root of the discriminant of the field. Okay. So this gives you a crude bound. You just take h, say that h is at least 1, and it tells you that the regulator for large enough d's and large enough discriminants will be less than constant to the power d times delta. Okay. And then you take an unramified extension L of k, so that the discriminant grows like a power of the given discriminant by the relative degree. Okay. And that gives you that the regulator of L is less than some constant, depending now only on the base field k, to the power L over q. Okay. So this tells you that you can actually construct number fields with small regulator, which of course implies by Boas-Siegel that they have a huge class code. Okay. So in some sense, this Zimmer's bound is also best possible, provided that you restrict yourself just to the degree. Okay. Okay, so now I discussed Daniel Bertrand's conjecture. So you take, you fix a subgroup, and you assume that the rank is bigger than 1, and of course less than Rk. And you use this determinant, and you use the Cauchy-Binet formula. So you sum over all the minors of cardinal n of the same thing that we used for the discriminant. And you defined it, so this is the co-volume of the thing. It's also the Lebesgue measure of the fundamental domain of such a lattice, sublattice. So in the special case where U is the full unit group, you recover the regulator. And you also recover the height, but not the Weil height that I described you. Instead of that, you recover the L2 height of the number alpha, which is that you take at the infinite places, you take the square root, the sum of the square root of the conjugates, the squares of the conjugates, the square root of the sum of the squares of the conjugates. Okay, so it's compared because you can compare the L1 norm and the L2 norm. It's almost the same. And you get something which is at least root d times the height, and of course, which is less than d times the height. So, but you don't control it. It's a norm comparison factor. You have a root d that lies in between. Okay, you have, let us continue. So now I frame the conjecture of Daniel Bertrand. So Daniel Bertrand asked whether there exists a M such that Cm is positive and such that the volume is at least a constant depending only on M for any number field with rank of unit group larger than M, and also whether there exists an epsilon in the unit group such that the volume of that given epsilon is at least C by square root of Rk. Okay, which is a version of lemma problem for the L2 height. So this is known since 20 years back with our joint work with Francesco Amoroso, and you have proven that 1 is true as soon as M is bigger than 3. Okay, and we have even proven something a bit stronger, which is in fact that the volume grows like d to the power m by 2 for any epsilon positive. Okay, and there is an implied constant that depends both on epsilon and m. Okay, so these statements are very strong if m is fixed and d goes to infinity and thus Rk goes to infinity. Okay, but as soon as you allow m to also vary close to Rk, well, it doesn't say anything because, in fact, the constant Cm also depends on d and could go to 0 faster than d to the power m over 2. So this is the whole point. Okay, so so I decide now what Villegas has suggested. So Villegas made the choice to stick to the L1 norm, but that's not. I don't think it's so significant. It can be these statements can be compared, and anyway, that's the choice he made. So the cause for that is that you don't have the proper notion of co-volume, but you just undo the exterior product K, kth exterior product of R sigma K with L1 norm, choosing the basic vectors for one given basis as norm 1 vectors and define the L1 norm compared to that basis. So you need to fix a basis for that. It's not completely intrinsic, but never mind, it works fine. And the conjecture was that whether there exist two constants with one bigger than one, such that the L1 norm is bigger than C constant times C to the n. So the prediction is that the growth is like in Zimmer's result, at least exponentially in n. And moreover, that the norm goes to infinity. Okay. So it is. So this conjecture is true for the full unit group. That's Zimmer's theorem, and of course it's completely open for m is equal to 1 because then it's again Lemma's problem. Okay. So what I suggest is that we restrict ourselves to pure wedges because then you really talk of co-volumes and you restrict to the L2 norms. And since if you do both, you recover the co-volume. Of course, for the L1, for rank 1, you lose the Weil height, but you have something which is very close, which is the L2 height. And then the framing would be for any rank M subgroup, do you have the volume bigger than C0 to some constant? And then whether you can require C1 to be bigger than 1. So this is a delicate question. Last time I discussed that when Waldschmidt was in the room. He told me, yes, whether if C1 is smaller than 1, then it goes to 0. And I'll try to explain you why the fact that C1 is less and bigger than 1 is not that important in my mind. But nevertheless, this is how Villegas formulated it. So we stick to this question and we'll discuss this point in a couple of minutes. So this is what I say. In fact, what happens is that if you think of Minkowski's theorem, the volume of the unit ball involves some gamma factors. Since they involve some gamma factors, even if you knew a full lemma conjecture or something, even much stronger than lemma conjecture, you would have something that goes to 0 as constant times d log d. Okay, so in fact, what you can essentially prove without too much tools is that this, if I go here, is that this volume is bigger than some exponential minus m log d. Okay, and so bring it back to exponential minus m is something which is already highly non-trivial. Okay, and so there's another thing is that Villegas doesn't require to stick to pure wedges, but allows any element in the lattice given by the mth exterior product of the unit group. So we'll concentrate on pure wedges and discuss first how to frame it in game. So this is we talk of of slopes introduced by Professor M.S. Narasimhan and Professor Arda in geometry context. So you take an Hermitian vector bundle, which it is because it's a Euclidean lattice. So it's a simple case of Hermitian vector bundle, and define its maximal slope. The maximal slope is just the infimum of the log of co-volume divided by the rank, and you put a minus sign. Otherwise, you put the max and you don't put the sign. And you frame it like that. So if you go back, yeah. So where it is? Oh, I should go up. You take the log, so you have constant times m. You divide by m, so you have constant. So you claim that the maximal slope is bounded below. Okay, by capital O of m. Okay, and so now what happens for non-pure wedges? For non-pure wedges, you have a comparison between the smallest norm vector and the maximal slope, and it involves again m log m, again exactly as what happens in Minkowski's theorem. So basically, if you prove the conjecture for the mu max, you still have something to do, because you still need to kill a log m factor to get the norm of any vectors. So you still have one step to go. Okay, but you are not that far away. Knowing the co-volumes gives you already highly non-trivial, at least if m is fixed, information on the smallest norm vector or the wedge, whether it's a pure wedge or not. Okay. And so I think that if you see that in this context, you see that whether or not the log C is positive or not is not that important. What is important is the m log n. Okay. So now I turn to higher dimensional lemma problem. So this is things that are 20 years old that we did with Francesco Amoroso. So you take a positive number, a point in the nth power of Gm, and then the claim is that the sum of the height is bigger than Cn over omega n. I'll define omega n in a minute. And in particular, this is easier to understand, that the product of the heights itself behaves like a lemma problem, 1 over d. Okay. So the definition is a bit involved. I'll quickly recall it. We don't need it actually, but just if you wish to use this statement as a black box, it's much more than enough for our purpose. But it's defined here. And you can see that this omega, if alpha is just a point, is just a degree. In fact, is just a degree of the point. So it gives you back lemma's problem precisely. Okay. So I won't comment on that. You have it on the slides. And so in 99, we obtained a lower bound, which was for the product of the heights, which was in terms of 1 over d log of d to some power with an uncomputed constant and a constant depending on m, which was also non-computed. Okay, and Amoroso and Villegas, a couple of years later, improved that with the explicit value of the implied constant, and also a much smaller, although it's already still large. It's you have a double exponent, or m to the f5 in exponent. But our original bound, if you had worked it out, would be like some m factorial in the exponent. So it's much stronger. and for applications, it's much stronger than the full lemma problem, because if you have two units, you multiply them, you still have essentially 1 over d, whereas lemma problem would give you 1 over d squared. Okay, but this, of course, still does not say absolutely anything on the case of dimension 1. So now we go to geometry of numbers. So you define mu k of m to be the max of the minimum of the product of heights of m multiplicatively independent algebraic numbers, or units in our case. And what gives you, what you get is that the volume of such a group is of the size d by m over 2 times mu k of m. Okay, so this comes from Minkowski. And it tells you especially why these kind of problems are beyond the realm of geometry of numbers. Because when you are with geometry of numbers, these implied this d and m are basically fixed. So you can just discard them. You have a 2 to the n or something that comes in, but n is a constant, so you don't care. And you know that the volume and mu k is essentially the same number. But in our case, they all go to infinity. And the value of mu k is also essentially bounded below by d, 1 over d. So the main term is the constant and not the product of the successive minima, which is here. So this is why one needs to be careful. Okay. And this 1 over m to the power m minus 2, of course, comes from the gamma factor, from the volume of the unit ball of dimension n. And so as soon as the rank is large, you lose a factorial. So you lose again a m log m, exactly as in Godon-Raymond. So in all these things, you have these m log m factors that plays against you, and you have to fight against it. Otherwise, you get absolutely nothing, no result at all. Okay. So what can we prove? The first result that we prove is that the Bertrand-Villegas conjecture is true for any rank which is less than d to the power 1 minus epsilon. And even more than that, we have something which is stronger, which is of the order of magnitude of d by n. You would excuse me for a minute. Okay. So, yeah. So now we go to some fixed fields, specific fields. So you assume that the field is totally p-adic, some given prime p. That simply means that all places over p are fully split. Or the field is totally imaginary. For example, it lies inside the compositum of the of all CM fields. In both cases, you can solve the full Villegas Bertrand-Villegas conjecture for p less than 7 or for p less than 31. Against these restrictions on p, I'll show you it later, come from the requirement that you want the C1 to be bigger than 1. If you allow C1 to be strictly positive, it's valid for any p. And if you have a CM field, it's also true, we'll tell it later. So now we want to tackle the case of subgroups which are of very huge rank. The rank is very close to Rk. In that case, we need to throw in some arithmetic constraint to beat this m log m factor, and you turn to relative units. So you go back to an old result of Friedman and Skoropa, which tells you that if you have a tower, K inside big K, then you have a natural subgroup, which is huge, which is those units for which the relative norm is root of unity. And Friedman-Skoropa proved again 20 years ago that this also behaves like predicted by the Villegas conjecture in constant to the power t. And recently, Chinberg, Friedman, and Sinnou improved that. And they proved the following. Assume that your subgroup U contains the relative units for some field. Then you have the Villegas conjecture, provided that the big field is large enough compared to the small field. The relative degree is huge. Okay, the precise statement is a bit better, so we will not discuss that. We want to have simple statements so that we can put them in slides. If you need the precise statements, I can always tell you. So what we did is something, well, it's on the same line, so it's the same statement. The only thing is that the relative degree now is only required to be at least the log of the degree instead of an exponential of the degree. So you gain about 2 exponentials, but you have the same statement. So, but I should stress that we thought of these kind of statements only after reading the archive paper of Chinberg, Friedman, and Sinnou. So they showed the lead. So now I'll go into, we still have half an hour, so I have time to discuss the sketch of proofs. I'll first go to the first results. So you go back to the Bertrand bound, which is here. And you plug in the Amoroso-Viada result here. So you are going to get a 1 over d times this log d factor. And this you expand it. And the 1 over d, you put it here, you get a -1, and you get some error term that depend only on n. As soon as you see this formula, you see that for large enough m, but small, this m to the power 5 will be much smaller than d to the m. And so it's going to be bigger than that. And then you need to do some calculus, and the precise value is the result of our computation that we did. We actually did the exercise, but it's actually an exercise. So the result itself is not difficult once you know the Bertrand's lower bound and Amoroso-Viada. And then you need to deal with the small values of m less than 8. And for that, even a weak form of lemma, which comes from the Bobolsky, say you take the bound of Paul Poutier, you plug it there and you get the full result. And this explains why it cannot reach the case where m is close to d, because when m is close to d, this error term m to the 5 is much bigger than the main term here. So it doesn't tell you anything. So now we turn to the periodic fields or the CM fields. So you say that a field has property B if the height is bounded below by some constant that depends only on the field. Okay, for any point. Here you can restrict to units. Say that it has property B for units if the height for all units is bounded below something that depends on the other. Okay, of course, this notion is useful only if L is not a number field but an infinite degree extension. Because if it is a number field, it's always true. This comes from Northcott. So there are plenty of fields which have this property. So some example is the abelian closure. This was proven by Amoso and Dornicic. You have also the totally real field. This was proven by Schinzel. Or for if you restrict to units, it's not true for non-units, but if you restrict to units, it's true for also for the composite term of all CM extensions. And in those cases, you have this explicit number that comes from the golden ratio. And so I give you the reference. And for totally periodic fields, you have, for example, the nice result of Pottmeyer that tells you that this is with the following bounds, it is true. But you see that the bound goes to 0 when p goes to infinity, because you have a log p by p. Okay, so this is what is going to prevent us from reaching the full Villegas conjecture with c bigger than 1 for large enough p's. So you just, again, you plug in Bertrand, and then you plug in Pottmeyer or Schinzel. So you have a bound of this kind. So this is bounded below. This is going to be big because d over m is always at least 1. So the whole question is whether you can ensure C1 bigger than 1. So again, it's an exercise, but it's not enough to prove the result that you have here, that I've given here, because the Minkowski bounds again are too bad. So where it is. For this result, for large p, you don't quite reach these values. But here you need only to have you don't need the full Minkowski. You just need the first theorem of Minkowski, where you bound below with the power of the first minima of the lattice. In that case, you have Hermite's constant, which is slightly better than Minkowski constant. So if you plug in Hermite constant, you get something which is slightly better, which looks like that. I've written the full thing, but you don't need to. So RK by D is essentially 1. It's 1 over 2 or something. If it's totally real, it's 1 if it's totally imaginary. So you have this m to the power 2. So here you have a small RK and m, so it's not too big. And so you have UL to the m. So if you compute that, provided UL doesn't go to 0, you have a good chance of getting a bigger thing. And this is how we prove the second result. Okay. Okay. So now we go to the third result. So I draw the following picture. So you have some subgroup which is large enough to be contained in the to contain the relative units. So you have a big volume. You have here you have a big volume. This is Friedmann's Europa, and you have your U which is sitting in between. So you don't know the volume could drop. It happens in lattices that you have a bigger thing which is inside two things with big volumes, but has a small volume inside, because you have some angle issues. But what plays for you is that you have only a small variation of rank, because here the difference of the rank between the two is the controlled by the unit rank of the small field. And if you allow k to go to infinity, the variation of rank is small o of the degree. Okay. So to show that the volume cannot collapse or increase very phenomenally, is that you have a key remark, is that the relative units and the units of the small fields are in fact in orthogonal complement. So you have an orthogonality relation. So this goes back to Bertrand. It's an easy exercise. You take two things. you compute the scalar product, and you use the product formula. You decompose the sum for places over the big field. You receive them sum over the places over small field and places over the big field. Then you factor that, and then you use the fact that the norm of the x, which is in the relative units, is root of unity. So the norm is 1 and the log is 0. So this is 0. And this gives you easily the orthogonality. And they are in complement because it's a rank computation. You show that the sum of the ranks is precisely the full rank of the thing. Okay. Now, given this orthogonality, you have an explicit formula for the volume. The volume that you are looking at, volume of K, is the volume of the relative units times the volume of your unit group that you're looking at intersected by K. And you have an index that is coming in, the index of the subgroup of U mod this the product of the relative units and the units lying in the small field. So now if you want to have a lower bound for that, you need, this is fine. This is Friedmann-Skorpa, this is big. So you need this to be not too small, not to bring the thing to 0. And this capital, that index not to be too big. If the index goes to infinity too fast, then it will kill whatever lower bound you have here. So these are the two issues that you need to control these two numbers. Okay. So these are the two things the two issues that you face. Okay. So you have a lemma. The lemma tells you that the index, in fact, is a divisor of the index of the decomposition for the full relative units. So UK divided by the sum of the orthogonal complement of the units of the small field plus the relative units. So what you have, so this is easy to prove. You just look at the map going to the quotient, compute the kernel, and since the map passes to the quotient, here you have this subgroup which maps injectively to that one, and so the index are divisible because you get the image is a subgroup of that other one. So now once you have divisibility, what you can do is to say, okay, I can use again the decomposition of, maybe I should write it down. So you have again, you have I prime times the volume of the relative units equal to the volume capital K of the small unit groups times the volume of the volume of UK. Okay, right. So you have this exact formula. So now we go back to the thing. So you have two exact formulas. The one that I showed you on the tablet and this one. And these two index are in divisibility. Using divisibility, you get that the volume of your unit group is bigger than the volume of the full unit group times the intersection that you have not yet controlled. It was the second issue that we faced. Times the volume of the relative units that comes on, that divides and nicely cancel out, and divided by the volume of capital K of UK. So you have this number that you don't control and this quotient that comes in. So there's a small difference here. In Friedmann-Skorpa, you have the volume relative to the logarithmic embedding for the small field. And here you have the relative embedding relative to the big field. That makes a difference. That's not the same volume. But still you are close. So this ratio is big. So what we need to do is to compare the volume of the unit of the full unit group of the small field when we go up in a tower, how it moves. And second, we need to get rid of the volume of the intersection, which was the issue that we faced always, that we saw in the beginning of the discussion. So the first question is easy to prove. You can show that if when you have a variation of the volume, it goes as a degree to the n. So it's not that good because it's capital D to the power m. So it's still exponential, and you have m times log capital D that plays against you. But still, m is small. So this is where we are going to use that m is small. So you have this ratio, and you compare that with small d divided by capital D whole power d. Okay. So we thought that we have this inequality. And now what you do is you say simply that this unit small group has rank which is less than d, and each individual vector is bounded below by Dobrovolsky's bound or Paul Voutier's bound. So you just use a one-dimensional thing, and you get something that goes to zero very fast, like a d factorial, but you don't care, it's a small d. So what do you get in the end? So you get something like an exponential minus d log d times an exponential minus d log capital D. Okay, log capital D is much bigger, so this whole thing is bigger than exponential minus d log capital D. And what you have for you have Friedmann's Europa that tells you that this is bigger than exponential capital D. So now, since small d is much smaller than capital D, you can kill that by bringing down this constant. So this is precisely what we do. And this completes the proof. So now we have 2-3 minutes. So I discuss a few things. First is that you can go to L1 norm if you want. And for that, what you define is the N1 volume. So instead of Cauchy-Binet, you forget the squares and you just put the sum. And you define the height of a subgroup like that one. That gives you another generalization of lemma, and can be probably interpreted in terms of adelic metric on the Hermitian bundle given by the rules of finity, by taking limits of L2 norms. I have not made that computation, but it looks like it's something like that. And so you get another version of higher dimensional lemma that again specializes to lemma problem in for rank 1, is that this height grows at least as fast as the degree of the field generated by the given units. Okay, so this is does not seem to be quite a consequence of a conjecture, higher dimensional version of lemma, but that would give for Villegas conjecture something like capital D to the power m times C of m. Okay, so this, and you have just one side of inequality. The product of the while heights is bigger than this height, but you don't have a converse inequality. You don't have a converse inequality for the time being. So I cannot see that they are both equivalent statements, but there is one side. And it gives you a motivation that if you further strengthen the lemma problems by predicting the growth of C of M, you probably have these Bertrand Villegas statements as pure pure consequences of the higher dimensional lemma, at least for pure weights. So I'll stop here, and we can go back to questions. So if I need to see, you can ask questions, of course, and I need to stop the screen sharing to see the questions. So I'll do that, but of course I'll put it back as soon as there is a question and we need to show the slides. And of course, if the sound is not good, you can put in the chat your questions.
Thank you, sir, for a wonderful talk. So, any questions here in the seminar hall? I think there is no question in the seminar hall. And some participants, any other question?
Yeah, you can either turn the mic or you put it in the chat.
Okay, it's okay. So any questions in the Zoom participant? So I think chat box there is one question.
Yeah. Yeah, tell me.
Michelle have asked one question.
No, it's not one question. It's just to say thank you, Sinnou. I learned a lot of things. So that was really good. I not know. There are many things that I learned. It's quite active now. Maybe I will ask a question.
Yeah.
In your paper of 1999 with Francesco Amoroso, the end of the proof was quite involved. It was quite complicated.
Yeah.
And how is it now? Is it easier or is it the same?
Yeah, it's much easier. Yeah, Amoroso and Villegas have simplified that. And in fact, I'll go back to the slides if you allow me for a second. I'll go back there. So where is it? Yeah, here it is. So you see, you have here a power which is m to the 5. And in our original paper, we had powers of factorials. So it was factorial to the power n or something like that. It was huge. And this was because the end of the proof was highly complicated, and the zero estimates were not enough to finish the proof, and we had to make induction argument. As Michel recalls, it was difficult to read and perhaps even more difficult to write down for us when we wrote down the paper. It was not an easy write-up. And they simplified that by using an argument which is somewhat reminiscent of what was done in the arithmetic lemma. I think it was by Louboutin or people like that, by using an arithmetic thing. So instead of working with the classical Siegel lemma, they worked with arithmetic Bezout inequalities. And that enabled us them to have a form which had a controlled height and a controlled degree. And then they performed induction. And thanks to the second information, they could kill this descent. So it is somewhat simplified now, thanks to, but it's still involved because you need to put in some deep arithmetic geometry in the construction of the auxiliary function if you want to do something. So I'll cut the.
Okay, thank you very much. Thank you.
So any question in the YouTube channel?
Yeah, you told me there was one.
No more questions in YouTube channel.
No, okay. So in that case, I'll ask a question myself and then I'll show you. If you allow me, I'll ask a question. So I'll go back. So There it is, yeah. Yeah. I go here. So from in the 1900 results, we showed that the Bertrand's conjecture was true as soon as m is bigger than 3. Okay. For m bigger equals 1, it is a lemma problem. We know it's a difficult question. And so for m bigger than 3, it's okay. So what happens for m equals 2? So this is the question. What can we say for m equals 2? So for m equal 2, if you go back to here, you have this 2 by 2 minus 1. So it kills that. So you have a d minus epsilon. So the whole problem comes from the fact that you have not quite lemma, but you have this log t factor. This d is fine. So you have precisely what you need. And this d goes against you. And so you have something which is 1 over d to the power epsilon. So you don't quite reach that. So and you see that you are at the limit. You would need a 2-dimensional version of lemma to be able to prove that statement. But there is a strange thing. So maybe I'll write it down in the slide on the tablet. So come here, and here I need to change page. So I make a new page. Yeah. So assume that Bertrand is true for m equals 2. Then Schinzel-Zassenhaus is true. Okay. So the interesting feature is that now Schinzel-Zassenhaus is true. This is known by Dimitrov. So you have Dimitrov, who has proven Schinzel-Zassenhaus. And you have Bertrand for m equals 2. That implies that. But again, the converse inequality is not known. And this comes from norm comparison factors between the L infinity norm and L1 norm. So you cannot go the other way around. First, I was very excited because I thought, okay, now that we have Dimitrov's theorem, maybe we can close the gap and tell that everything is true for m equals 2, but you still have some work to do. So this is the answer for the question.
Thank you, sir, for the wonderful talk.
Thanks. Thanks a lot.